Hello students, how are you? Hope you're doing fine. So at this stage, um, welcome to this class about regression. It's part of regression is nowadays often part of machine learning, but regression is an old method which is still very useful also to analyze big data or not so big data. So the project is with a small data set. I think it's the best way to start learning it. This is a joint course with Greg Mayer. Anyhow, so here we go. Let's see. Aha. So, with a view towards machine learning simply means that a lot of time nowadays, what you do, you look in the data for rules to predict or categorize things, and you try with your data what works best, and then you use this for prediction of future events, and you avoid overfitting with cross-validation. So we'll see how this works, but this is great because you can understand in this manner regression. And there's a more traditional approach, which in many places actually amounts to the same, but more traditional statistical approach is calculating many things, and this approach here is very simple to understand because you just look for prediction in the data set and look what works best. So there's a project, as you know, you're working on it, and there are only 60 houses with selling prices, and you need to find a way to predict selling prices based on feature like square foot, bath, number of bathrooms, type of house, and so on, and the neighborhood given as a zip code. And why 60 houses only? It's the best way to start, I think, with a small data set. Later one can do a much bigger data set. But so here there's not the selling prices are only in a small time window. So there's not a problem of additionally trying to predict prices, which are say in the next 2 weeks given data for 10 years. Because otherwise you would have to see the evolution over time of the house prices to be able to factor in the houses which were sold 10 years ago. But so here to start with, there's not this problem of time because the data is selling prices for a very short amount of time. But the small data project is I think interesting because in reality a lot of what we do has to do with small data. You can have a million homes prices given to you, but when you predict a house in a certain neighborhood of, for example, Atlanta, then bingo, this million houses is not as valuable to you as 20 houses sold in the last 2 months in that neighborhood. In that sense, these 20 houses in the neighborhood carry enormous amounts of information, more than probably a million houses through the country. So anyhow, even if you have the big data, part of it is to predict in an optimal fashion with very restricted data set, because the most important houses to predict one house is going to be sold in the next month is maybe 20 houses in the same neighborhood. Okay, so here, house price prediction. How much could we expect for our house? We've not yet sold it, but we see 3 houses here in my little data set sold, and they are, say, in the same neighborhood, and selling price is 6, whatever the units are. The living space square feet is 2 for the first house. The second house, selling price 10 square feet, living space 4. House number 39, that's 4. Then our house, we have not yet sold it, but before selling it or putting it on the market, we would like an estimate. And we use the data, and we see that we have 3 square feet, and our house is going to be on the market. So how can we use the data to predict? Oh no, I pressed the wrong button. So here we go. We use a linear regression rule, and later we'll see that we can make more general rules, but the rule is alpha plus beta times square feet. And we'll be able to use other rules, that's not very important, but first we use such a prediction, and what we do is simple. We find the alpha beta, these are the parameters, yielding the best prediction in our data set, and then having those, we denote them by alpha hat, beta hat. See here, these are those which do the best job at predicting in the data set. We predict the new selling price, which is predicted price is alpha hat plus beta hat times square foot living space of our house, which has not yet been sold. So, and how do we define a best prediction? We can measure, you have to measure how good we do in the data set. So we can, for example, measure the average error size. We take the absolute value of the errors. For example, here with alpha and beta given, the prediction would be alpha and beta times 2 for the first house, since square feet living space is 2 and the selling price is 6, so the error there is this 6 minus alpha plus beta times 2, and we take the absolute values. Then we make the average of all three houses. We calculate the error. Here we have the error of the second, third. We divide by 3, so that's the average error. So one way is to just say we want the average error to be as small as possible and determine in this way alpha and beta. And then we apply this to determine here for our house the selling price. So here we determine the coefficients alpha hat, beta hat, which minimizes average error, and the predicted price for our new house is alpha hat plus beta hat times 3. So we can also, I like to put numbers there, because often you see these complicated formulas and you don't understand really that in principle when we look at the parameters alpha beta which we have to determine, the equation or function to minimize is very simple, because it's only as a function of alpha and beta. The others are just numbers. So here yi would be the price of house number I, xi the feature here, the square feet, the living space, and here is this average error, which is the sum of these error absolute values, so yi minus alpha plus beta xi. Okay, we could measure in different ways. We can, in Zillow and so on, they always evaluate how good their algorithm is of predicting selling price of houses by relative error. So we could use a relative error. It wouldn't change much. Still go in the data, just look where does that relative average error in the data, where is it minimized. Another favorite one is sum of square error. So you take the squares instead of taking the absolute values. That's how traditional regression is done, because with that formula of not minimizing the absolute values, average error, but the square, you can explicitly calculate very simply just by derivative, setting derivatives equal to 0, what the solution is. So traditional regression is often done with sum of square errors, minimizing the sum of the squares, for historical reason mainly, because in the old days you couldn't just search like nowadays with gradient descent and computer. You don't care so much, but back then it was invaluable to be able to just explicitly calculate the best solution, and that can be done when we use sum of square error. Why would this work? If the prediction rule works well on the data set with past selling prices, then we hope it predicts our house well. So we have, of course, we cannot predict a house in Switzerland using an Atlanta database. And the other problem is it will work as long as we don't do overfitting. If our house is similar than the one in the data set, the prediction error should be similar. So we can just look for different rules, how good they work in the data set, and that gives us an indication if our house is similar to those in the data set of how good the rule will be in our data set, except overfitting. So overfitting is simply simple to understand. We'll also show you more of the math, but The way it works is you have a huge, say you have a huge collection of possible features. You could say hundreds of things, and you just search and search and search. In the end, you'll find something which, in our little small data set, will coincide by chance uh, with what we want to predict, but does not really work well on the new house. We'll see more of that later. So why should we use linear prediction at all? We used predicted price is alpha hat plus beta hat times the square feet, the living space. Why should we? Well, uh, here the answer. This is a real data set of your project. You see, you have different colors for each neighborhood, for each zip code, and you see clearly they are on the line, on a straight line. So that's the answer. You see in the data more or less how it behaves, and here you wouldn't use a quadratic function because when you plot it like that, if it's quadratic, you'd see more or less it looks totally different. So that's funny because in traditional statistics, you're not supposed to look at the data too much before and so on and so forth. But we'll talk about that in the second part on regression, which is more formal. But in real life feature engineering, you go through everything, you look, and many of the things you see right away. For example, when I look at this data set, I see price is proportional to square feet, and it's not a quadratic function, for example, of square feet. So the reality of it, not necessarily the theory, is that at least when you do feature engineering, you look at everything, you plot it, and you try to understand it. Now note here that price is linear pretty much, and then because these points are not that far from their lines, but if you would like to predict this as one line for all three neighborhoods, you would do a very bad job. So this is a very typical example of real life feature engineering, where you go in a data set and understand what is happening. If you just try to use one regression line for all three neighborhoods, you would get very bad results. So again, the answer is we use linear approximation because that is what we see in the data. Or maybe you know it. If you've worked a lot in real estate, you just know that this is more or less linear. If the data would like quadratic, we use a quadratic function, by the way. We could have then predicted price equals alpha plus beta plus square foot living space square. And that wouldn't change much because in your data, you just change the column with square foot living space by square foot living space square. You just square all the entries of that data column and then proceed exactly the same. So then it would still be linear. The predicted price would be linear, but linear in square foot living space. So it wouldn't change much. Now let's go through it one more time. I do it very slowly because this is really the basics, and then when you understand this well, it's all of machine learning, all the other algorithm can be understood in quite similar fashion. So try to find a relationship in the data below of the type selling price is equal to alpha plus beta living times square foot living space plus beta garden times square foot garden. So with the parameters, the Greek letters here in green, alpha, beta living, beta garden, and our little data with four houses and the selling price and the living space and the garden. And yeah, we want to find such a relation which is best. So let's find a linear relation, and we find that there's an exact relationship which is true for the four houses. Selling price equals 2 square foot of living space plus 1 square foot of garden. So in this case, we would have alpha equals 0, beta living space equals 2, beta garden equals 1. Now, this is too good to be true. You can check. So you calculate for each line, and you see selling price equals 2 square foot living space. For example, here 7 equals 2 times 3 plus 1. Correct. 10 equals 2 times 4 plus 2. But that's almost too good to be true, because in reality you can never predict absolutely correctly the future selling price. since there's a randomness in it. When you buy a house, you bargain, and the outcome is a little bit random. So in most cases, there's no exact linear relationship. Note that each house leads to, if you wanted an exact linear relationship, each house would lead to a equation, and well, I forgot the alpha here, and you have less parameters and equations. And in a real data set, you wouldn't have 4 houses, but maybe hundreds, maybe thousands. So there's no way to find an exact relationship, except if you have many features. So with longer data sets in general, no exact linear relationship can be found, more equations and variables. Now, let's see a linear relationship makes an error. Just take the linear relationship like before, but now a more realistic situation where in the data set is no exact way of prediction. So the linear relationship I look at is 2 times square foot living space plus 1 times square foot garden should be the predicted selling price. And so here I have, for the first house, the selling price is 8, for the second house it's 7, third house it's 8, fourth house it's 7. Now, this is no longer the exact selling price, but say a predicted price. So I have 6 as a predicted price because I took 2 times square foot plus 1 times square foot garden. So 2 times 2, 4, plus 2 is 6. Then here, predicted price for house number 2 is 7, since 2 times 3 plus 1 is 6 plus 1, 7. And then the third house has a predicted price of 10, that is 2 times 4 plus 2, that's 10. And finally, the fourth house has a predicted price of 7, 2 times 2 plus 3. So with that, you see there the prediction is not perfect. There are discrepancies. Here for the first house, a discrepancy of 2, and of the third house, a discrepancy of 2 also. So here, these are the prediction errors in the data set 2, 0, 2, 0. And so now we can average the prediction error. So average prediction error in the data set 2 plus 0 plus 2 plus 0 over 4 is 1. And we can write this explicitly here. This is the error of the first house, the error of the second house, the error of the third, the error of the fourth. And I quickly want to introduce this notation. We'll use always y for the quantity to be predicted, in our case, the selling price of the ith house, yi. XIL is a square feet size of living space, XIG be the square feet of the garden of the ith house. The formula for the average error is then pretty much as before. Here is the first error, that is the selling price of house 1 minus the predicted price of house 1, and here the second error in absolute value is y2, the selling price of the second house, minus this prediction for the second house, and so on. The 4 errors, absolute value divided by 4. So whereas the whole thing is that we're simply going in the data to look for the best such linear prediction rule by minimizing that, say, average error, which amounts to the same, to minimize the sum of the absolute value of the errors. So we want to find parameters alpha, beta living, beta garden, minimizing this prediction error in the data. As mentioned before, we could also use a sum of square error. That is, we minimize the sum of the error square. That is traditionally was used in regression because it allows to explicitly calculate things. So here I'm going to show you how these calculations are done now with sum of square. Now we can actually solve the problem. So we want to minimize this function, and remember the x's and the y's are just numbers. So the only thing really interesting is alpha, beta, garden, beta living. And to minimize, we put the derivatives equal to 0. And then we calculate this, and we get a very simple formula. We set the equal to 0 derivatives, and now the beauty of it all is this might look pretty complicated, but it's not, because these sums, they are just a number. And so when you have such a sum, it looks complicated, but it's just a number. By the way, this would be the dot product. If I take the features as vectors, this would be dot products. But that's not important. You see, these sums, they're just one number. Now, it can be complicated with x and different x's and the indices summed and so on. But in the end, this is just only three unknowns, and it's linear, a system of three linear equations in alpha, beta living, beta garden. So something extraordinarily simple. And even if the data is huge, so we can rewrite this in matrix format here, and each one of these sums is just an entry of a little small ridiculous 3 by 3 matrix. So we have, for finding the, even if I have hundreds of houses or a million, this thing here is a ridiculously small system of three linear equation with a matrix here of 3 by 3, and these sums will just be a number. And so now I could see that this above here, this thing, so this can be written as x transpose x, and this can be written as x transpose y. X is a matrix of the data without the prices included, and the first column is ones for the, if we have an intercept, if we have alpha here. So we take the data matrix, and then we have this formula here. Well, x transpose x is just going to be 3 by 3. Actually, it's going to and here x transpose times the selling prices. And so this is ridiculously simple to program in NumPy, for example, because you just take the data matrix x, augment it for the ones without the selling prices, and then you can in NumPy multiply x transpose with x and x transpose with the vector of the selling prices, and you get a simple linear equation which NumPy can solve for you. Y represents the vector of the selling prices. And now here you can put this on the other side by taking the inverse of this product matrix, and this is a classical formula solving when we want to minimize sum of square errors, finding the parameters which optimize this solve. It's a very simple explicit formula, and even if the data is huge, as long as the features are few, this is very, very simple little equation. So again, I repeat it one more time. We find parameters alpha, beta living, beta garden, minimizing the mean square error or sum of square errors, and we estimate them by, they're called estimates, and we'll see later that they can also be viewed as maximum likelihood estimates in certain cases. And then to predict a new house, which has not yet been sold, so we don't know for how much it would be sold, but we are considering, is it worth selling? What will we get? And so we just apply the linear formula with our parameters, which were best at predicting the house in the data set, hoping that they would do a good job at predicting our house. And of course, for that, we, at this stage, later stage, we can consider more complicated situation, but at this stage, we need the houses in our data set to be in the last 8 months or so. Later we'll see how to also integrate houses from the past, that kind of information. But that's more complicated because you cannot just make an average, for example. And why would it make sense? Well, of course it's strange, you think. It's easy to predict the selling price which are already known, but our goal is to predict something which is not yet known in the future. So does this make sense? One way of looking at this is risk minimization. So for that we assume all the data random. So we see x1 is a feature vector, so square feet, bed, bath of the first house. y1 is the selling price of the first house. x2 is a feature vector of the second house, y2 the selling price. And we assume these kind of random vectors, which are independent and all follow the same model, then what we want is, say we work in real estate and we want on average, long-term average, to minimize the error. One times we make a bigger error, one times we make a less. It's random, obviously, but we want it to be as small as possible in absolute value. So long-term average in a probability model, when I throw a die many times, build the average, that's going to be the expectation. So here, the expected error, long-term average is expected error. So we want the expected absolute value here of y minus this prediction to be as small as possible. In other words, we want to find the parameters minimizing this expectation. That minimum is called the risk. Or actually this function here of the parameters is called the risk, and we want to minimize it by choosing the parameters, minimizing it. So, and we don't know, we can have a model, then we could calculate what would be best to minimize that. But here is an approach without knowing how the probabilities of these random variables, what model they follow. And that's very, very useful, because in real data, indeed, often you don't know exactly the probabilities. So here we say an expectation is just the long-term average. So if I throw a die many times, build the average that's about the expectation, provided I throw the die many times. Well, here this expected absolute value of the error is thus approximately the average of the absolute value of the errors in the data set. So since it's approximately the same, we minimize not the expectation, which is what we would like to minimize, but instead we minimize the average error in the data set, which, if the data set is large enough, is going to be very, very close to that expected value. And that is called this in data set average is called the empirical risk. So we minimize the empirical risk because with large data set, empirical risk is very close to the expectation here, which is the risk. So it amounts to the same, except when we overfit, as we'll see. Just quickly a remark, in traditional regression, we don't assume the features to be random. Because, for example, if you have a house and there's a swimming pool, that's not random. You don't throw a coin to decide whether or not it should have a swimming pool. You sell that house and it has a swimming pool. So there the model is, and that is in the next class, that price yi is random, that you have this formula, again exactly like before, and then you have a random term which is with expectation 0. So in other words, you would have the expected value would be this linear formula, or another formula if you want, whatever, of the features, and then several houses with exactly the same features, that is with the same square feet for the living space, square feet of the garden. They have an expected value, but their price are different, so we cannot say what the price will be. We can only say what the expected price is. If I had many houses with exactly the same feature, well, it would be given by this formula, and because each of these houses has an independent random term with expectation 0. So there's a random fluctuation, if you want. It's as if I have the formula, that would be what I expect, but now it's a random fluctuation for each house which has exactly those features. So for each house having exactly those features, I throw a die to decide if it's a little bit more or a little bit less, like a random error with expectation 0. So again, too many features will mess up the prediction. The reason is that when we look long enough, we always find some silly rules which seem to predict in our limited size data set selling price. A best example is fund managers. You have a fund, and you look for those who do really well in the last couple of years, and that will be maybe 20% out of 100. Now you look for their name, their first name, the many things. In the end, you find something which by chance seems to correlate with those who do over better, and then the next 4 years that won't work. So that's called overfitting. When you look for 100,000 for thousands of different relations, in the end you find something just by chance, but that will not help you predict the future. And in linear regression, we can understand overfitting very, very well. Not just talk about it, but actually mathematically, because you can put n houses and p features, and then usually you have an exact solution that is zero error in your data set. And that's overfitting, because in reality you cannot predict a house perfectly since it's randomness. When I buy a house, maybe suddenly we make a deal, you give it a few thousand less, but I buy right away. That cannot be predicted in advance. So there's no way you can predict perfectly, but in the data set, if n equals p in general, you can predict perfectly. So here's an example. We have 3 houses and 3 features. Well, that's 3. If I want to predict this perfectly, exactly, I have 3 equations with 3 parameters. Usually, 3 parameters, n parameters in an equation can be solved in a unique way, leading to 0 error. So that's an extreme overfit with 0 error in the data set. Here in this case, beta living is 3, beta garden is 2, and beta is 1. So the prediction error in the data is 0, but that does not correspond to the reality of predicting future houses. And that's the only problem, because as long as the prediction error in the data set for a rule is similar to the one for predicting new houses, we are in business. Then we can choose the rule which works best. But when something, just because we looked for too many rules, works too well, then yeah. So, small overfitting example, prediction error for future selling price is not 0, never. And so this is an overfitting. We can do cross-validation, that's simple. We split at random the houses in a training set and a testing set. And so we choose the parameters on the training set, and then even if we do overfitting there, the testing set being independent has not been overfitted. So we try it there on the testing set, and we'll see if we have been overfitting. So you can randomly split the data. So here I have a data, and I flip a coin, maybe for train and test. And for each house I flip here, the first house will be in the training, the second in the testing set, the third in the training, the fourth in training, the fifth in the testing set. And so now I have the green data, the green training set. So I will try to fit my parameters on the training set on the green data. And then ultimately, to really know how good it is without any overfitting, I will go to the red data, of course, and try it there. And there is no overfitting, so it will be an unbiased estimate. And feature engineering, how many features should we add? Well, we do that on an additional such set we set apart called validation set. At least in theory, that's how you should do it. So you add to feature which are best at predicting first. Then maybe first is a neighborhood, and maybe the second best is to be used together with neighborhood is probably square feet. Then you can see what comes next. Should we add bathrooms or number of bedrooms, whatever? So you start like that, and at each then you need the validation set, because you're going to add one feature after the other, and to choose the next feature, you take the feature which you have already chosen and see what works best. And then you get the list of such features which you add one after the other. Now, when should you stop? Because at one point you will have too many features and you'll fit. And for that, you have now the validation set, because on that validation set, you will see at what point when you start adding, it gets worse. Your prediction gets worse, and that's when you stop. And then finally, you go into the testing set to really know an unbiased view of how good you are, because in principle that procedure with the validation set could already lead to an additional little bit of overfitting, but that's really to be very precise. So then once you have found how many features to add using the validation set, at each set when you add one more feature, you check on the validation set how good now your prediction is using that amount of features, and that when on a validation set the estimate gets worse, the error becomes worse of your prediction rule, then you stop, and then to know really how good you are, you finally do the final evaluation on the testing set. So in the data we see regression depends on the zip code, on the neighborhood. So this interaction between selling square feet and the zip code. And we can work with each neighborhood separately, but sometimes there are features which are still the same. For example, it could be that bathroom, adding a bathroom costs the same in each neighborhood. So the formal way to do this is we do the zip code as a categorical data. So that means first you have to notice that here I have a zip code 9,000 something and 3,000. So it's not because the zip code is 9,000 that the price of the house is 3 times more. So this is categorical. So we do encode it in a binary way. So for each zip code we need one vector. So that will add quite a few parameters. So we see here zip code 94043, and we have the vector 1 1 for those houses in that neighborhood, and 0 0 everywhere else. And then 30309 is another possible zip code in our little project. So we have a vector 0 0 1 1 0 0, which is 1 only where the house is in that given zip code 30309. Finally, for 30310, we have a 0 1 vector telling us which houses are in that zip code. Now, when we have an interaction, we have to take the product between these feature vectors. So we have the linear regression depends, as we have seen, the linear regression depends on the neighborhood. We see the different color neighborhoods, they have completely different regression lines. So to formally, you could just work on each neighborhood separately, apply regression separately, but here we're going to do it more correctly. That is, we get the mixed effect, that is multiply simply the square foot with the neighborhood. So here square foot 2 3 with that neighborhood vector, which was 1 1 0 0, leads to this guy. So this is the square foot vector times the vector for 94043. By times we multiply each entry and get a new vector of the same length. Here square foot interaction vector with 3039, simply take the zip code vector, which was 001100, multiply with the square feet, that is, we get 0042 because we have 4 2 here, 0 0. And finally the interaction vector for the zip code 30310 with the square feet vector, well, square feet 5 and 3, 5 and 3, and otherwise everywhere 0. So now we can rewrite this as predicted selling price is beta 1 times that product vector between square feet and the neighborhood 94043 plus beta 2 times that interaction feature between square feet and 30309, and beta 3, and so on. And here we see the ith house interaction feature is simply obtained by doing the product. We do that for each of these 3 interactions. We just do the product of these vectors. We get 3 new vectors, and that's very simple. And then we can write the whole thing in one equation, because if a house is in the neighborhood 94043, then this interaction for 30309 and 30310 will be 0, so it will be a regression just for that neighborhood. So this is the same as doing a separate regression in each neighborhood. Here put the intercept alpha 0, because often this is quite reasonable for house prediction. Anyhow, one more thing, the prediction rule looks linear because we saw it in the data. If it were not, it wouldn't be a big problem. Say, for example, the best way to predict would be using the function xi, zi. So xi is a living square feet, zi is square foot of the garden of house number I, and the function would be x squared plus 2xz plus z to the power 3. Complicated function, and not at all linear, but that doesn't matter. We can still use linear regression by simply uh, uh, putting x squared, 2xz, and z3 as 3 additional columns in our data. So we add these 3 columns, x squared, so 2xz and z to the power 3, and bingo, we get again a linear regression. So that's the beauty of linear regression, that it even works for when the best prediction rule is not at all linear. And so by best prediction function, we mean that it would minimize the risk. So here the long-term average, that's the expectation of price, which denoted by y, minus h of xz. So h of xz can be any complicated function of xz. If this is minimized by f, that is the best prediction rule, here x is a square foot living space and z is a square foot of the garden, y is a selling price of a future random house. And that's not important, but the point is we can just now write this as a linear prediction rule, provided we add to our data set square foot living space square and one column, which is obtained by multiplying square foot living with square foot of garden, and then finally one column square foot garden to the power 3. And in principle, we can if we can add the powers and interactions we want, we can model anything because of Taylor. Remember, in Taylor, you can approximate, at least if f, the best prediction rule, f of xz is smooth, then you can approximate it by a finite polynomial. And then you add these terms of the finite polynomial and bingo, except that may lead to many features and make some overfitting. So that may request large data. So to finish, one last remark is that when you have factors, say you have 9 type of home, 5 possible values for number of bath, 3 zip codes, that's 3 times 9 times 5. So if you have interactions there, that means what the bath adds probably is different in each zip code, in our case certainly, and for a type of home maybe also. So then you have to multiply to have all these interactions with 3 with different categorical data. That becomes huge. You would have 135 such interaction vectors. So that's out of control. So that's the only problem. And if you have huge data, it shouldn't be such a big problem. Otherwise, there are techniques to alleviate that. Thank you for your attention, and that's it. Bye-bye.